So welcome back, and today's March 13th, and today's daily LeetCode problem is called Symmetric Tree. Now what you're given here is a binary tree, and we want to see if it's symmetrical. And so another way of describing it is if it mirrors itself across its center. Now there's a couple of different cases here. The first one is, okay, what if we're dealing with nothing? And in that case, we actually want to return true because nothing in itself is symmetrical, I guess. That's just interesting to me, but that's what the expected result here, and I kind of get that. I think that's fairly intuitive. And so, okay, what if we're dealing with one node? It is also symmetrical because one in itself, if you kind of mirrored one thing, it'll look exactly the same. So in that case, it's also correct. Now, okay, what if you're dealing with a tree like this, where you have 1, then 2, but then it has no right child here? Then that would be false because you would expect 2 to mirror with another node with the same value of 2. And so in this case, it would be true. So if you have a tree like this, that is true. Now, okay, what if you're dealing with a value of 3 here? So then that would be false, because you would also expect it to carry the same value. Okay, so that's false. So essentially 2 rules. You want, if you have a child on the left, you expect a child on the right with matching value, okay? And so the next thing is, okay, what if we're dealing with kind of multiple children here, or a larger subtree? And so the basic rule, and once you kind of think of it, it's hard to forget it, so hopefully if you ever see this in an interview, or I don't know, if you're solving symmetric trees at your job or whatever, you remember it. But you want to compare I'll just kind of make it look better here, the left subtree. So say this is the left subtree. You want to compare it with the right subtree. Okay, so this is kind of the right subtree here. This is the left subtree. And you want to compare the left subtree's left node, this one here, with the right subtree's right node. Okay, and so those values match, so that's good. And then the second rule is that you want to compare the left subtree's right node with the left subtree's left node. Okay, and so I'll just kind of write that out here. So compare left subtree's right node with, I'll just kind of space it, right subtree's left node, like that. Okay, and then vice versa is, okay, if we mirror this logic, is we want to compare the left subtree's left node with the right subtree's right node. Okay, so that's the act of mirroring itself, and this relationship is kind of gonna act recursively. Okay, so you can't really see that with this basic example. So if we, there we go. If we kind of expand this example and say, okay, what if we have 1, 2, 3, 4, and then 4, 3, 2, 1, this is correct. So this also would be symmetrical. And so let's look at this kind of bigger example. So when you're at this subtree, then you would expect its left node to match with this right subtree's right node, and it does. And then from there, because we're doing depth first search, we would then look at, okay, then we would expect this subtree's left node to match with this subtree's right node, which it does. And then you would also expect this subtree's right node to match with this subtree's left node. And then we would want to look at, okay, from here, this subtree's right node to match this one's left, and it does. And then continuing on, I'm running out of colors, but this one's left should match with the right subtree's right node, which it does. And then finally, this one, you'd match this left subtree's right node with the right subtree's left node. And so it kind of recursively happens if you kind of expand this to another level. I think eventually when you're drawing it out, it'll make sense to you, okay? But maybe slow this down, relook at it, but the core logic here is compare the left subtree's right node with the right subtree's left node, and the left subtree's right node with the right subtree's left node. I think I got that right, but great. So, and that's how you check the mirror logic. So I think that's most of it there. We're going to do two different solutions. One is recursive and one is iterative. They both have the same they both have the same time and space complexity. It'll be O of n for time because you'll be visiting each node once. And then in the worst case, because this isn't a balanced binary tree, and you're not dealing with like a binary search tree, like it could just be a very linear tree. So you're dealing with O of h for space, because that will be kind of the recursive stack, or how much will be in your, for the iterative solution, in your actual stack. And so in the worst case for space, it's O of h. Okay, so let's go ahead and write the recursive solution. So let's write that out. And so what this looks like is, okay, let's handle that first case where, okay, what if the root doesn't exist? Then we want to return true, because nothing in itself is actually symmetrical. So if you're dealing with nothing, it's symmetrical. Otherwise, we want to use a helper method. So let's return a helper method, and we want to compare the left subtree and the right subtree. Great. And so then we have this helper method, and let's say, okay, we have left and right. This will represent kind of the root of the left subtree, which say you're here, and then you're comparing, this will be right, okay? And so now what we do, and we don't even have to compare the root, say here, because we know that when you're dealing with one node, it will be symmetrical. And so now what we're gonna do is say, okay, what if we're dealing where they're both null? And that's important because when you kind of reach the bottom here, at the leaf node, you want to make sure that when you're dealing with nothing, null, if they're both null, then you want to return true in that case. Okay, so if not left and there's no right node there too, then we want to return true. Now in the case where, okay, what if one is null and the other isn't? That doesn't work because you want them to match and both have nodes. So if the left subtree has a left node, then the right subtree should have a right node, say in that case. So if not left or there's not a right node, then we'll return false. So it is not symmetrical. So otherwise what we do is say, okay, we want to make sure they have the same value. So we know they both have nodes, but do they have the same value? So we can store that in a variable, just to make it look a bit cleaner. So is the current symmetrical? Is it currently symmetrical? So we say, we know that if they both have the same value. And then finally, we're going to return a combination of our three cases. So we want to make sure they have the same value. And then we want to recursively look at those two scenarios that I talked about, and I'll show you that here. So we want to recursively look at the left subtree's left node and compare it with the right subtree's right node. And, oh, I just have to call self here because it's not a function. And let's grab the helper method again and compare the left subtree's right node with the right left child. Makes sense? And so let's try running that. Accepted. And that is the recursive solution. And so now let's go ahead with the iterative solution. I think I usually like the iterative way. I'm not sure why. It just usually comes more naturally for me, writing out the code. I don't know. I think recursion is just more challenging for me. And so let's grab a stack. And so we're going to use a tuple. Oh, and I almost forgot, we want to check that base case. So if there's no root, let's just go ahead and return true immediately. And that helps us avoid having an exception when we're checking its children. And so we'll add the left and right here. And then we say, okay, while there's something on our stack, let's pop it off. So this grabs our left and right subtree, or the root at our left and right subtree, I think is a better way of thinking it. Let's pop those off our stack. And we say, okay, if we don't have a left and we don't have a right root, then let's just go ahead and continue and keep going, because there's nothing there, and let's just pop that off our stack. It's all good. Let's continue on from there. However, if there's not a left root in that subtree, and our right subtree doesn't have, or our right subtree doesn't have a root, then that's the case where, okay, we have one node on one side but not on the other, so we return false. And return false. And then finally, okay, let's say, what if their values don't match? Well, let's return false immediately there. So if the left subtree's root has a value that doesn't equal the right subtree's root value, then let's go ahead and return false immediately, because we know it's wrong. And then finally, we're going to kind of do that, what we had that recursive logic, but instead we're doing it iteratively, so we won't be dealing with a recursive stack, we're actually dealing with a real stack here. And so let's just append to our stack the same core logic, which is comparing the left subtree's left child and with the right's right, and then kind of invert that with right, left, right, and right, left. Okay, and if it makes it all the way through all that iterative logic, we just want to return true, because it made it through the entire tree. This is just because I'm dealing with a tuple, and so I just need to wrap these in brackets. Perfect. Great, and that's the iterative solution. So that's today's kind of daily LeetCode problem. I hope it helped, and good luck with the rest of your algorithms. Awesome. Have a great day.